Welcome to another explainer. Today, we're diving into something that, at first glance, usually looks like a chaotic, dense web of engineering data. We're talking about centrifugal pump curves. But don't worry, we're going to completely decode this together. By the end of this, you'll be able to build a crystal clear mental picture of how to read and interpret these vital charts, meaning you won't even need to be staring at a graph to understand exactly what your equipment is telling you. Okay, let's dive into this. Here's our roadmap for today. First, we'll cover the language of pumps. Second, the 3 core curves. Third, we'll give you 5 steps to read those curves. Fourth, we'll walk through a real-world example. And finally, we'll wrap up with pro tips for safe operation. All right, section 1, the language of pumps. Before we can decode the data, we really need to understand the alphabet it's written in. Our first foundational metric is flow rate, which engineers represent with the letter Q. This is typically measured in cubic meters per hour. If you want a really simple way to conceptualize this, just think of flow rate as the speed on your system's dashboard. Just like miles per hour tells you exactly how fast your car is flying down the highway, Q tells you the exact volume of fluid your pump is pushing through the pipes over a given time. Next up, we have head, represented by the letter H and measured in meters. This represents the total dynamic head of the system. Now, in everyday terms, this is basically your system's lifting requirement, or the total pressure resistance it has to overcome. If flow rate is your car's speed, well, head is the steepness of the hill you're trying to drive up. It's literally the total energy your pump has to deliver to lift and push that fluid to where it needs to go. Finally, we have power, represented by P and measured in kilowatts, alongside efficiency, represented by the Greek letter eta, which is measured as a percentage. This totally completes our dashboard analogy. Power is your fuel consumption. It's the sheer amount of electrical energy the pump needs to do the work. Efficiency is how well it's actually using that energy. You want to find that absolute perfect operating state, the optimal gear, so to speak, where you get the most flow and the most head for the least amount of wasted power. Let's move on to section 2, the 3 core curves. Now that we've got our variables down, we need to translate how they actually interact when the pump is running. And this brings us to a huge fundamental question. How do these core variables interact as your system demands more flow? I mean, if you open a valve to get more speed, what exactly happens to your hill climbing ability and your fuel consumption? Getting a mental grasp on this dynamic is the master key to the whole thing. So let's paint a mental picture of this classic trade-off. Imagine a graph. Along the bottom horizontal axis, you have flow, increasing from left to right. Now picture the head curve. As flow goes up, that head curve fundamentally slopes downwards. Why? Because as you push more fluid out, your overall lifting capability drops. But on the flip side, picture the power curve on that same graph. The power curve climbs steadily upwards as flow increases. So as you move more fluid, your pressure drops, but your energy demand steadily rises. It's a constant balancing act. Now, what's really fascinating is how the efficiency curve ties all of this together. If you picture this curve on our mental graph, it doesn't just go straight up or straight down. It arcs upwards like a hill to a peak, and then it drops off again as flow gets too high. It's visually showing you exactly how efficiently the pump is converting your kilowatt power into actual hydraulic energy. And that peak, the absolute highest point on that arc, that is your operational holy grail. We call that the best efficiency point, or BEP. All right, section 3, 5 steps to read curves. We have the vocabulary and we know the rules. Let's transition from theory into practice. So if you're looking at a dense grid with multiple lines crossing over each other, it can honestly be a bit overwhelming. How do we actually pinpoint our exact operating point on this complex grid without getting totally lost in the data? Well, let's walk through a rock-solid, simple framework. Here is how you trace it out, step by step. Step 1, know your requirement. You literally can't start without knowing your required flow rate, your Q, and your total dynamic head, your H. Step 2, locate that required flow rate on the horizontal axis at the bottom. Step 3, draw a visual line straight up from that point until you hit that downward sloping head curve we talked about. If you look straight over to the left axis from that spot, you'll verify your head. Step 4, from that exact same vertical flow line, look at where it crosses your arcing efficiency curve and your rising power curve, and simply read their values on the right side axes. Step 5, that specific spot where your required flow and head meet on the head curve, that is officially your operating point. Section 4, a real-world example. Let's pivot seamlessly and put these 5 steps to the test with some real engineering numbers. Imagine you're designing a brand new system. Step 1 says we need to know our requirements. Let's say our required flow rate, our Q, needs to be exactly 200 cubic meters per hour. That's our target speed. Now we add the second crucial piece of the puzzle. To overcome the friction and elevation in our particular piping system, our required head, RH, is 60 meters. Awesome! We now have our two starting coordinates, a flow of 200 and a head of 60. By mentally tracing those inputs through our steps, finding 200 on the bottom axis and going straight up to where it meets 60 on the head curve, we lock in our operating point. Now, from that exact vertical line at 200, we check the other curves. We see it intersects the efficiency arc at roughly 78%, then we drop down to where it intersects the rising power curve, look across, and see it requires about 35 kilowatts of power, and boom! Just like that, we've extracted the exact energy and efficiency outputs based solely on our initial inputs. No magic, just mechanics. Let's bring it home. Section 5, Pro Tips for Safe Operation. Because finding the data is one thing, but knowing how to use it safely is what really matters. Here are 4 golden rules for safe pump operation based on everything we've learned. First, absolutely always try to operate the pump as close as possible to that best efficiency point. That is where vibrations are the lowest and your component life is the longest. Second, avoid operating at the extreme low flow or extreme high flow ends of the curve. Pushing it to the edges can seriously damage the equipment. Third, always ensure your available net positive suction head, or NPSH, is strictly greater than your required NPSH. That prevents destructive cavitation. And finally, always use that power reading we just found, like our 35 kilowatts, to guarantee you select a suitably sized motor. You definitely don't want it burning out under a heavy load. So, we've taken what initially looked like an intimidating, tangled grid of lines and translated it into clear, step-by-step logic. The relationship between flow, head, and power isn't random at all. It's highly predictable once you know how to build that mental map. I'll leave you with this thought. Next time you face a dense, technical graph, whether it's for a pump, a compressor, or an entirely different system, what conceptual steps will you use to isolate the variables, find the trade-offs, and translate that data into your own simple, actionable dashboard? Thanks so much for exploring this with us, and keep actively applying these mental models to the world around you.